Hi everyone, this is Sami. I'm here to present our work on automatic discovery of composite SPMD partitioning strategies. So what's the composite partitioning strategy problem? Recently we have started to see a trend in growing the neural network models into very large sizes. So we can see some of the recent examples, for example, Palm models like 540 billion parameters. These two neural networks now started to face the problem of how do we scale our accelerators to face the challenges of training these large models. To enable the training of these large models, there have been several developments in the system side of things, how to parallelize these models. Batch parallelism is one of the simplest examples where you split the data and send it to multiple instances of the model. Model parallelism, for example, Megatron enables transformers to scale to very large sizes, and so on. There are many different techniques used for different architectures and different set of problems. And here where our work fits in. We provide Automap, an automatic composite SPMD partitioner for research workflow. Our main users are researchers. They work on a diverse set of accelerators and they actively develop a new model architecture on this. They tend to have mix of interest in system and machine learning expertise. Hence, we need a solution that works on device, on host, runs for a couple of minutes before it finds a reasonable solution. And we are limited by the computational power on these devices. Hence, we cannot just use a large model and fine-tune it for a user program. Our search operates over the MLAR of the neural network representation. Once the user provides a neural network, we trace it into MLAR, which then exposes all the operands and how they are being used in the neural network, which could be a very large model. In our previous work, we explained how we reduce the size of the module by only considering the worklist, which is basically what an expert would use for partitioning a model. It consists of the input parameter and the optimizer state. And another feature our compiler provides is the ability for it to propagate partitioning rules to other operands in the module, depending on the program state and specific propagation rules. And despite all of that, we still have to consider a very large number of choices at every tiling decision we need to make. And this problem is even more pronounced in the composite partitioning strategies domain, as our previous work looked into only a single axis. Now we are considering multiple axes. Each axis provides a new dimension to the problem, where the search needs to consider whether to partition on the first axis or the second axis or the third axis, which argument on which dimension. So the search problem is exponentially, it grows exponentially with the number of axes we need to consider. Our main insight is we can decompose the problem into smaller, more manageable search problem by rather than looking at it as a global optimization, we look at it as a local search for a specific goal encoded by the user. For example, if we want to discover data parallelism with zero like a Megatron, we could word it as such that we tell our search to search over a batched axis, improving runtime, which will yield something similar to data parallelism. Then we tell it to search over the same axis, the one that discovered batch, but tries to reduce the memory, and it will discover something similar to zero like partitioning. And finally, if we want to discover something like Megatron, we tell it to look over a different axis than the one used for the batch parallelism, and we look for something that improves runtime without reducing memory. And that leads to something similar to Megatron. These high-level goals decompose the search space rather than the search looking over all the possible dimensions on every axis and every argument. Now we only consider one axis at a time when we are searching, and allows us to provide smarter way of budgeting the search. We also provided enhancement to our MCTS to allow it to explore in this large space. Our first one was utilizing the idea of our powerful info propagation can yield a similar module even with two equivalent different actions. For example, if we tile the argument 0 on dimension 0, axis 0, Argument 1 on dimension 2 on the same axis will get tiled through infopropagate. So that leads us to having two different states with equivalent final module. We use a forward analysis after doing a tiling, and we create a snapshot of what has been tiled and use that as our state, which allows us to basically duplicate the states we have in our search, and to have a single state for both actions that yield the same work list. And similarly, based on that idea, we also discovered we could also group these actions. So now we know that there are two actions that lead to the same state. If we don't, so we encode that information in our search, which allows it to basically combine these two actions and consider them as a single equivalent action, and gives the search the budget to explore areas that it has not explored before that we know will yield to a different tiled work list. So we tested how these enhancements work in enabling our search to discover composite search strategies. On a Transformer 24 layer, we were able to discover batch parallelism, Megatron, and zero almost all the time using a goal-oriented Monte Carlo. Adding action grouping and state alias and compressed state, we were able to do that even more reliably without using a metacontroller, which is the goal-oriented Monte Carlo. We were never able to actually recover these composite search strategies, which makes it which makes us believe that goal-oriented Monte Carlo is crucial to discover these composite strategies that are otherwise very difficult to find. We evaluated our work on real hardware. For transformer use case, we had the two devices. For the UNet and GNS use cases, we had 8 different GPUs. Our evaluation on the transformer showed interesting results. Looking at runtime 1, runtime 2, memory 1, which is in the one in purple here, this is a search strategy that's looking for improving runtime on the first axis, improving runtime on the second axis, and then improving memory on the first axis. This yields the same partitioning strategy as if we have done batch parallelism, Megatron, and zero. But also the user could encode different preferences. For example, if we look at the light purple or pink, where the user specify they want to improve runtime, but they want to improve memory on all axes, which yields a model which is 1 gigabyte smaller than any other partitioning strategy. It is much slower than the others. It's a trade-off the user has to make, and this could lead to interesting follow-up work where we try to look at these different trade-offs the user would like to do, and maybe we can provide them the option to decide which of the final solutions they would like to use. Similarly, we found that GNS and UNet, actually, our automatic partitioner are able to discover very interesting strategies that non-conventional, in a sense that if we simply apply batch parallelism, batch parallelism and zero, we do not find it as performant partitioning strategy as the one our automatic partitioner is able to discover by using the composite strategies encoded. This is a preliminary exploration of using goal-oriented Monte Carlo search. So we ended up using an assumption where we have enough budget to fully explore a single goal. We assumed a fixed budget for each goal to be, for example, an evenly divided budget, search budget. So if we are looking at our MCTS to discover batch parallelism, Megatron, and zero, there is a lot of time. There's a lot of wasted trajectories after the search has discovered batch parallelism, we know it's not going to find something better, and still it spends 1,000 trajectories trying to find something better. One way to address that shortcoming is by trying to search for the goals rather than trying to use the goals to guide the search. So we try to formulate the problem as a Monte Carlo tree search over all possible goals we can discover, which yields a formulation similar to the one we have been using already, but now rather than like searching over a specific partitioning we try to have a search over search, which tries to figure out the objective or the goal we have discovered in the current local search. So in summary, our search is built together with our PartIR, an IR rewrite engine, which allows us to make use of compiler-specific tooling to compress our Monte Carlo tree search space, allow us to do action grouping, and then we also enhance our MCTS with a goal-oriented search to allow us to discover composite partitioning strategies and allow us to explore in these exponentially growing multi-axis search problem.